Is my voice clear or not? Do you have my voice? About desktop, you can see the PowerPoint file and PDF file. Yes, of course. Thank you very much for your answer. In last session, I have talked about earthquake resistant design. According that I stated, if a building is enough to resist to the earthquake, then such building is called earthquake resistant structure. You know what is the earthquake resistant designs know and definitions of the earthquake resistant design according that's explained and described in the last sessions. I have talked in last session about the some earthquake resistant structure techniques such as base isolation method, energy dissipations devices, seismic dampers, and keeping building of trust. In the last session, based on I have taught about the resistance techniques. Base isolation devices, and that's an instrument or a separate building from ground by some rubber devices. And we had seismic dampers. The seismic dampers are special devices. These devices introduced in the building and absorb the energy of earthquake and produced by seismic wave to the resistant to make the resistance buildings. And I have shown some the resistance buildings and using these techniques in these buildings in last sessions. We had dampers in 3 types of dampers to design the resistance buildings such as viscous dampers, friction dampers, yielding dampers. I had talked in last sessions about these dampers, viscous dampers, friction dampers, and yielding dampers. And you saw some shapes and pictures about these techniques. I had some case study in last sessions to more informations and your knowledge. Last session I had talked more about the resistant building, more in the structures upper than foundations resistance, and today I want continue about And that's discussions. What is the goals of earthquake resistant designs? It is economically not feasible for ordinary buildings to the design as absolute earthquake proof. However, the goals for EQRD, earthquake resistant design, shows in this slide. We have 3 types earthquake design, as shows in these diagrams in this slide. First type of earthquake design is serviceability level earthquake. This is for frequent and minor earthquakes. In this level, building should not be damaged and continue to remain in service. And in this level, expected 10 times during the life of buildings. This level of earthquake called serviceability earthquake. Another level earthquake design is the damageability level earthquake. In this level, we have oceanal moderate earthquake, and no structural damage is expected. Non-structural damage should not lead to any loss of life. And in this level, expected once or twice during the life of buildings. Last level of earthquake is a safety level earthquake. In this level of earthquake, in this type of earthquake, that's called safety. We have rare major earthquake. Building should not collapse. Non-structure and structural damage should not lead to any loss of life. You can see this slide, the earthquake types as serviceability, damageability, and safety levels. And the details and definitions of each level of each earthquake types. Okay, this slide shows the resistant earthquake resistant design based off building shapes. In symmetrical building plan, the distance between center of most mass called COM and stiffness center or center of resistance we can call COR is less compared to symmetrical plans as shows in these shapes. Irregular building configuration results in a twisting or torsion of rocking when subjected to the seismic forces. As you can see in these schematic shapes in this slice, you can see the asymmetrical plans as COM, center of mass, and as symmetrical plans as CO or center of resistance, as shows in these shapes. These shapes, we have the symmetrical plans in COR. And if you can see, as the center of mass is the out of the shapes. Direction, you can see direction of ground motions. And internal resistive force due to a structure element configurations act through COR. Equal and opposite parallel forces produce couple based on COR. But inertia force due to earthquake act through COM. The COM is out of the shapes and cannot not help the resistance design. Base of a building shape, we have three type asymmetry shapes. Asymmetry in geometrical asymmetry that can occur in plan of buildings or elevations of building or building joints. Another type asymmetry for building shape is stiffness asymmetry, and the third type is mass asymmetry. And after that, I have described about these three type asymmetry in the plan: geometry, stiffness, mass asymmetry in the building shapes. This slide shows the geometry, asymmetry, and symmetrical in the plan. In the first slides, in the first schematic shape in the slide in top, we have asymmetrical plans in geometry models. Asymmetrical plane undergo a large amount of torsion and has extreme corner are subjected to heavy force. As you can see in these shapes, and asymmetrical plans in the geometry avoid asymmetrical building like I, L, U, and T-shaped buildings. Another schematic shape in downside of this slide shows some shapes, and they have symmetrical plans in geometry plans. As center of mass or center of resistance, shows in the plan twist will not occur due to the earthquake. Building will need to resist the horizontal inertia force only. Symmetrical plan like rectangular, square, polygonal, or circular, or variable, as shows in these schematic shapes, shows circular and square shapes. In these shapes, we have symmetrical plans we can use for earthquake resistance design based of geometrical resistance design. Another type of geometrical asymmetry is geometrical asymmetry in elevation of the buildings. In this geometrical asymmetry in vertical direction, sudden change in stiffness or mass creates instability. It attracts more forces and hence undergo large deflection. Excessive deflection induces large bending moment and shear force in the structure member, as shows in these shapes. In left side shows the geometrical asymmetry elevations. You can see stresses connection zone with red color connection. You can see in vertical direction sudden change in stiffness or mass creates instability. And in left side, in the elevations of the building, gradual change in lateral stiffness and building floor mass in vertical direction be provided based on this elevation geometrical symmetry. Another type of geometrical asymmetry is in the building joints. You can see in these shapes and occurring after twist moment in the visual CG axis of buildings blocks, and typical problems occurs in the junction area as two neatly boarded block restrict each other and try to separate out in the periodic motions, as shows in these schematic shapes in this slide. Solution of these problems: for solve these problems in geometrical asymmetry of building joints, building blocks can be separated by a seismic gap, as shows the schematic shape in the downside of this slide. As for example, the individual building, you can see the individual building blocks now vibrate in the plan separately. The stress concentrations in block joints can be avoided. and you can see in the block joints as a seismic gap. The stress connection in the block joint can be avoided, and building block can be separated by seismic gaps. Another asymmetry in building shape is stiffness asymmetry type 2. As shown in this building, you can see the stiffness plans as COM, center of mass. You can, in the first plan, the COM is the same COR in the this concentrated in same point, and you can see the line of resistance that in the COM or center of mass and center of resistance. In next shapes, the center of mass is different, a bit of center of resistance, and then horizontal deflection. We have a horizontal deflection of column twisting at rough level about center of resistance. You can see the first shape is a correct shapes as stiffness symmetrical plans, and the right side shapes is incorrect the plans as stiffness asymmetry for design the resistant building. Another, the resistance buildings design is based off the mass symmetry. As shown in this slide, the correct mass symmetrical shapes plan, and you can see the mass asymmetry in the right side as incorrect plan shape. In the left side, you can see differences in COM, center of mass, and center of resistance, while in white torsions couple, which produce instability in the plan. These big problems in the building under earthquake force. As mass asymmetry. In another slide, you can see the deals of the building foundations as problems. The foundations of buildings under earthquake forces can occur in the building and destructions in the buildings. We have two big problems in building foundations after the earthquake occurs. First, problems in the foundations. We have differential settlement. And second problem is liquefactions under the earthquake forces. And these problems give the collapsing and failure in the building after the earthquake occurs. We have three type solutions to solve these problems: differential settlement and liquefactions. One technique is type beam, another using raft foundation, another type technique to solve the differential settlement problems is base isolations. This slide shows differential settlement, the resistant inertial force in the superstructure cases uplift and compression in the flat foundation at different ends as shows in these shapes. And if we have different shell settlement in base of the buildings, give the sliding or overtraining in the buildings after this occurring the different settlements in the foundations as shows in this schematic shapes and picture in these slides. The tightening of foundations due to uplift force inertia, the failure of foundation or building or occurs as shows in this schematic shape. In this schematic, as you can see, we have loose soil after earthquake occur. We have compact and consolidate in the loose soils during earthquake and change volume during earthquake in the loose soils, and after then occurs different settlement in the foundations, and then we have the problems in the columns and building the upper of these foundations as overtraining or collapse in the structures. You can see resistant inertia force and uplift and compression, and after ground acceleration under earthquake forces. Another problems coming in the foundation after liquefactions under earthquake forces. We have three main prerequisites for liquefaction occurring. First, a layer of relatively low sand or silt in the site plan. Another prerequisite for liquefaction is a water table high enough to submerge a layer of low soils, and another main prerequisite for liquefaction is an intensity of ground shaking sufficient to increase the water pressure between soil particles to cause the soil water mixture to liquefy. If we have these three main prerequisites for liquefaction, the liquefaction after earthquake can occur and give destructions in the buildings and structures after earthquake. These main three prerequisites for occurring the liquefaction and important. In the liquefaction, temperature generated during the large earthquakes with many shaking can cause the liquefied sand and excess water to force its way to the ground surface for several meters below the ground, as shown in these pictures. You can see destructions, buildings, destroyed buildings. The phenomenon may incorporate both flow of already liquefied sand from a layer below ground and a quicksand effect. This phenomenon of liquefactions occurring after the earthquake. We have two major problems in the foundation may cases after earthquake. One is differential settlement in foundations. Second one was the liquefactions occurring in the foundations. And we need to solve these problems before occurring the earthquake forces. We can solve this problem with the tie beam or raft foundation or base isolations in the foundations. Isolated foundations. In isolated foundations, isolated foundation is one way to solve the differential settlement in foundations. In this solutions, individual footings should be interconnected with tie beams or a structural slab to prevent any relative horizontal movement occurring during earthquake shaking. As shown in this shape, you can see the detail of the isolated foundations and the material columns, slab footings. Another way to solve the differential settlement problem in foundation using the raft foundation. As the raft has a common base and it equally and uniformly distribute the superstructure load to the subsoils. You can see in this schematic shape the concrete raft. This concrete raft, it sprayed concentrated loads onto a larger area and makes the structure tolerant of the minor ground subsidence. It mobilizes the entire weight of the building to resist inertia, induce overtraining movement, and you can see in this schematic shapes, concrete wrap and columns of moment frame. In the raft foundations, equally and uniformly distribute the force, the superstructure load to the subsoil and reduce the earthquake energy, absorb the energy of earthquake and give structures and build. Another way to reduce differential settlement in the foundation, use the base isolations in the foundation of buildings to reduce the earthquake energy and absorb the earthquake energy. As that described and explained before in last sessions about the base isolations, you can see the schematic shape, the known isolation buildings after the earthquake occurring, and the base isolation building after the earthquake occurring. You can see the known isolation building after earthquake occurring give the destroy in the building and destruction in the building. But base isolation building safe and no destructions. You can see the shape of base isolation in these pictures and the materials of the base isolations in the foundation separated in the between the column and the foundation used to absorb earthquake energy and reduce the energy to transfer the column. Please just a moment. Okay, another slide shows the techniques for making earthquake resistant structures in the base of structure. Resistance. Currently, there are several design philosophies in earthquake engineering, making use of experimental results, computer simulations, and observation from past earthquake to offer the required performance for the seismic threat at the site of interest. There are five broad categories of structural systems which are taken into account when designing earthquake resistance buildings. As shows this slide, some of techniques for making earthquake resistant structures, bearing wall system, using bearing wall system in a structure, using building frame systems, moment resistant frame system, dual system, cantilever column systems when in designing earthquake resistance buildings. Okay. First type using bearing wall system. A structural wall located road the structure provide primary vertical support for the building's weight and that of its content as well as the building lateral resistance as shows in these pictures. Bearing wall buildings are commonly used to residential construction, warehouse, and low-rise commercial buildings of concrete, machinery, and wood constructions. You can see the wood construction in these pictures. Unlike standard masonry walls, which are solid, the interlocking mortar-load machinery blocks allow a slight movement and lock tighter over time, aided by an innovative application of steel reinforcement. This construction technique is also better at dissipating the energy of a seismic wave that traditional machinery. Masonry building, you can see it in these pictures. Another way, bearing frame systems, as shows in the picture, for design the building resistant. For buildings constructed of a structural steel or concrete, lateral resistance is provided either by diagonal steel members or hermet brace that extend between the beam and column to provide horizontal rigidity, or by concrete, masonry, or timber shear wall that provide lateral resistance but do not carry the structure's weights. As shown in this picture using the bearing frame system such as steel material shows in the pictures. In some building frame structure, the diagonal braces or walls form an inherent and evident part of the building design. In most buildings, the braces or wall may be hidden behind exterior cladding or interior partitions. You can see in these pictures for building concentrated of structural steel and concrete lateral resistance is provided either by diagonal steel members, pyramid brace, another way using moment resistant frame. Moment resistant frame used for both structural steel and reinforced concrete construction, as shown in these schematic shapes. The horizontal beams and vertical columns provide both support for the structure's weight and the strength and the stiffness needed to resist lateral forces. Stiffness and strength are achieved through the use of rigid connections between the beam and column that prevent these elements from rotating relative to one another, as shown in these steel frames. Moment resistant frame systems are popular because they do not require brace frames or a structural wall, therefore permitting large open spaces and faces with many on of structured window opening, as shown in this the schematic shape structures shows in these slides. Another type for resistant building design use dual systems in the structure of construction structure in the buildings. Dual system is an economical alternative to moment resistant frames are commonly used to tall buildings. As shown in these shapes, you can see dual frame configurations and single frame configuration. You can compare the displacement, horizontal displacement between the dual frame configurations and single frame configuration as shown in this slide. You can see this placement increase in the single frame configuration compared the dual frame configurations as shown in this slide. Dual system structures feature a combinations of moment resistance frames and concrete machinery or steel walls or steel braced frame can combine this dual system structure with moment resistant frames and concrete masonry or steel walls or steel brace frame to increase the resistance of the building structures. The moment resistant frame provide vertical support for the structure's weight and a portion of the structure lateral resistance, while most of the lateral resistance is provided either by concrete masonry or steel walls or by a steel brace frame. As you can see, these schematic shapes in dual frame configuration steel and single frame configuration, and you can see delta H display as displacement. You can see the delta H displacement in dual frame configuration less than the delta H displacement in single frame configuration based on the resistance moment resistant frames. In this slide shows some earthquake building code in Japan based on earthquake resistant structures. Japan is a seismically active country and has some of the most rigorous earthquake building standards in the world. This earthquake building code used in the Japan to making earthquake resistance structures. Standard 1925 earthquake resistant construction regulation were introduced case in earthquake. Effect of this standard regulation for wooden beam reinforced concrete used in construction in town areas. And standard 1950, the introduction of the Building Standards Act, a Tashin. This case 1948 Fuku earthquake. In effect, regulations were no longer limited to town area. And standard 1971 amendment to the acts, sharing reinforcement and reinforced concrete foundations. You can find these standards on the internet, and you can compare these standards with your earthquake country standards. Your standards in your country, and you can see what's the difference between these standards and your country standards. Another earthquake building codes in Japan 1981. This is standard for new earthquake resistant building standard, and you can find in the internet. You can study, and for more information, I can refer you to internet to download and study this standard. Another slide show one case study in Shigeru Bin's paper tube school. This homework of the students in the university to design the Shigeru Bin's paper tube school. Shigeru Bin, along with a term of Chinese and Japanese students, built a temporary but resilient schools out of paved and bicycle cars, board using some recycled material to design this school. This shows the tile of this school. Recycled paper tubes are molded into load-bearing columns, bent into truss, and rapidly assembled, and then can be made waterproof and fire resistant. Various thickness and diameter of paper can be adjusted to support more weight. Can be if you just on a case study designed by students just for more information. You can use some recycled material to build the structures as a homework. You can also use some idea. In this school, for framework made from paper tube walls made cheap material, easy to produce, and roofs made of polycarbonate relations. This one case study has a feasibility use material that are available anywhere in the world and is also structurally sound. Also, you can find behind of your hometown or your city some recycled material or rubbish material as recycled. You can use for build the strength resistant buildings under earthquake force. Okay, also we had some way to earthquake resistance designs as the sole problem foundations after the earthquake occurs and to reduce the differential settlement in the foundations and liquefactions in the building to reduce the energy of the earthquake. and we can make the building resistance as structural materials, and using the resistance building techniques. So some I have explained and described about some type of resistance building shapes as geometrical symmetry, math symmetry, or resistance moment. And we had some techniques for making earthquake resistance, such as bearing wall systems, building frame system, moving resistant frame system, dual systems, cantilever column system that I have explained and described today about these techniques. You can, for more inertia, for informations and study more, you can use the internet and some of sources as book and articles, papers. About that I stated today. For your homework, you can find the earthquake buildings codes and standards from others country and compare with your country earthquake buildings code and standards, and see the difference between these standards in your country and others country and compare between them. If any questions, I can hear and can answer your question. Please let me know your questions. Okay, I think for today is enough. If you have no questions, we can finish today class a little early, and we can continue this deal in the next sessions, and I will send you the PDF of this that I describe and explain today in your WhatsApp group. You can study and you can, for more information and search in the internet and other sources and books. Okay, that's enough. And thank you very much. And goodbye. See you the next session of class in the next week. Thank you very much.
You are currently the only person in this conference.